guys, let's talk about continuity and how it relates to limits. First, continuity is a very important idea for us here as we branch into calculus because there are a lot of very important foundational rules for calculus that only work if a function is continuous. It's important for us to be able to determine whether or not it is. So take a minute here and decide for these 4 graphs in your warm-up which of them are continuous and which of them are discontinuous. So we've talked a little bit about continuity over the last couple sections. We didn't really get into it deeply, but we mentioned the idea that if a function is continuous, we should be able to draw all the way through without picking up our pencil, right? So this function, continuous. This function, oh, not continuous right here at this value, right? I can draw this part, but then there's a hole that I have to jump over to draw the rest. So this is discontinuous. And we say that the point of discontinuity is whatever this x value is right here. So it's actually, let me change this. It's much more common for us to see specific x values here given as a. So let's call that x value a. And then right here, this one, let's see, this all looks good until I get to this point, and then I have to make a jump in my graph, right? There's a break here where I have to move to the other piece. So this is discontinuous right here at this x value. How about this one? Well, this part's okay, all these values are continuous, but then I have to jump over this value where my function is, well, my function is defined here at the x value a, but it's not defined in line with the rest of the function. I have to kind of jump up here to grab that point and then come on back down. So this is discontinuous also at that x value a, so this is discontinuous. So what we're going to investigate in 11.3 is not really so much is this whole function continuous or discontinuous, but we're going to be investigating is it continuous at a particular x value. So for example, for this x value a, is it continuous right here? Well, it's continuous at that x value if I can draw through that x value from the left side through that point to the right side without picking up my pencil. So we're continuous at a here. We're not continuous at a here because I have to draw from the left side, jump over that hole, and then to the right side. We're discontinuous at a here because, well, can you see that the problem is even though that point is defined, we do have an x value here, or rather a function value for x equals a. The trouble is that I'm approaching a different value from the left side and the right side. So what we notice here is that the limit on the left side is different than the limit on the right-hand side. So we're approaching 2 different values. Here, for this last one, we are approaching the same value from the left and the right, but the trouble is when we get to that place that we're approaching from either side, that's not where I actually have a point. The point is actually above it. So, first of all, a function, a whole function is, a function is continuous at a particular x value. In general, if we can draw through that point from one side to the other without picking up our pencil, we talked about that here in our warm-up. But what's going to be more important for us to be able to do here as we lean toward calculus is to show a proof of why it is or is not continuous. And that takes 3 things, which we were talking about a little bit up here. So a function called f of x is continuous at an x value called a if it meets these 3 conditions, and it has to fit all 3. First, the function is defined at this a value. So I actually have a point there where x equals a. The limit as x approaches a for that function has to exist. So keep in mind that means that I have to be headed to the same value from the left and the right-hand side. And third, the limit as x approaches a has to be the same thing as the function value. So let's come back up to the top of the page here and talk about each of those 4 examples we had and if it meets qualifications 1, 2, and 3. So for this first example, the first thing I want to know is f of a defined? Yeah, I have a point where x equals a, so it is defined. The next thing we want to know is, does the limit exist? The limit exists if, as we approach a from the left and as we approach a from the right, we're headed to the same place. I am, right? The left and right hand limits agree. And then the third thing, the value of the function at a has to be the same thing as the limit. So effectively, these first 2 have to be the same value. And that's true here. The actual function value is the same thing that we're approaching on either side. So the function, the value of the function f of a is the same as the limit as we approach a. So it is continuous at x equals a. This one, we want to know first, is f of a defined? So right here is a, look at, oh, I don't even have a point on my function there. There's that open hole. So it fails right away. F of a is not defined. So already I can say that it's not continuous at x equals a, or that it is discontinuous at x equals a. I don't even have to check the rest of it because it failed the first one. Next, this one right here, the first thing I'm checking is f of a defined? Sure, there's a point at x equals a. Right there, it's defined right there. The next thing I have to check is the limit, oops, sorry, here number 2, is the limit existing, which means am I approaching the same value from the left and the right? I fail there, right? The limit doesn't exist, so it cannot be continuous at that x value of a. Look at the third one. My first check is the function defined at a? Here's a, yep, it's defined, I have a point there. The second thing I check is, does the limit exist as I approach a? So I check from the left and the right as I approach a. Yep, I'm headed to the same spot. And then third, is the limit the same thing as the value of the function? No. Look, I'm approaching from both sides, this value right here where the hole is, but the actual function value is up here. So it fails on the third one. So we can see that by this definition, this 3-point check or proof, that we can see the very same thing that we could see just by checking the graphs, visualizing it. So it was easy enough to see here with the graphs what was happening, whether it was continuous or not, but understand that when we're asked if this function is continuous or that function is continuous, we will be unlikely to see a graph. We'll be given a function rule or equation, and we'll have to determine it from that. So let's get some practice. Okay, so we want to know, in our first example, is the function f of x, which is defined this way, continuous at x equals 2? So we remember that we have a 3-part check. The first thing I have to check is this function defined at x equals 2? Can I actually find a value there? So let me try, what is f of 2? So f of 2 is equal to 2 times 2 plus 1 over 2 times 2 squared minus 2 minus 1. So let's see, we get 4 plus 1 is 5 in my numerator. And in my denominator, I've got 2 squared is 4, times 2 is 8, minus 2 gives me 6, minus 1 gives me 5. So 5 over 5, 1. So it is defined. We do have a function value where x equals 2. Next, I want to know, does the limit exist? Now, what we're asking is, am I approaching the same value from the left and the right? So remember from lesson 11.2, our last lesson, that the first thing I should always try is direct substitution. Can I find what I'm headed to as I approach an x value 2? Can I find the y value I'm approaching just by plugging it in? Does anything funky happen there? No, we just saw that, right? We saw plugging in 2 directly. It gave us 1. Super, I can do that. The limit as x approaches 2, let's see, I don't want to write it like, yeah, I do, okay, of 2x plus 1 over 2x squared minus x minus 1 is equal to, I'm direct sub here, 2 times 2 plus 1 over 2 times 2 squared minus 2 minus 1 is equal to 1 again, just like it was above. So the work there looks similar, but understand that we're showing something different. Here we were showing exactly the value of the function when x equals 2. Here we're showing the value that we're approaching from both the left and right hand sides, where we're approaching x equals 2. Now, fortunately, we were able to do that by direct substitution, which is the easiest way, but it does mean that it looks a lot like that step above it. So my third check is it continuous? Well, it's continuous if f of 2 is the same value as the limit. And it is, we got 1 here and we got 1 here, so it is continuous. So here's what I have to say, and we're thinking about like how I would have to express this next year in calculus, since some of us are headed that direction, and that's what we're getting ready for here. So I'll say, because f of 2 is equal to, the limit as x approaches 2 of the function, which is 1 in both cases, then f of x is continuous at x equals 2. Literally, we have free response questions on our AP exam almost every year, which ask us to do exactly this, show in a 3-part proof that a function is continuous at a particular x value. So we already know how to do that. Guys, we're on our way to scoring a 5 on the AP Calc exam. Okay, next example. Notice that we have the same function, but this time we're asking, is it continuous at x equals 1? So let's try it. Again, we've got a 3-part check here. Is f of 1 defined? So I literally want to see the value of my function when x equals 1, 2 times 1 plus 1 over 2 times 1 squared minus 1 minus 1. So we get 2 plus 1 gives me 3. 1 squared is 1 times 2, so 2 minus 1 minus 1. Oh no. Now I don't want to say this equals 3 over 0 because I can't actually, this thing doesn't exist, right? So I'm going to say it leads us toward that, or it would imply that, but this is undefined. So right there I failed. I have to pass all 3 parts. I just failed at showing that f of 1 was even defined. So does the limit exist? It doesn't even matter. I'm going to skip that part and go straight to saying no. F of x is discontinuous or not continuous, either phrasing is okay, at x equals 1. Now there are a whole bunch of places where it is continuous, but x equals 1 is not one of those places where it's continuous. It's discontinuous there. So we're investigating lots of different x values here. So no, f of x is discontinuous at x equals 1 because f of 1 is not defined. So let's take a little bit closer look at what's happening here. If I graphed this function, well, the first thing I might want to do, because it's a rational function, right? I have a fraction or a quotient there. I might want to factor it and see what I can find here is going on with the denominator. So if I do that, if I factor it, notice I've got factors 2x plus 1 and x minus 1 both in the denominator. Those are both points of discontinuity on my graph then. We know that from algebra 2, right? So because this 2x plus 1 is on the top and the bottom and it could cancel out, it represents a hole on our graph where 2x plus 1 equals 0 or x equals negative 1/2. There's a hole in my graph. This x minus 1, because it's only in the denominator, I know that it means that I have a vertical asymptote where x minus 1 equals 0 or x equals 1. So those are points of discontinuity on my graph. So if I'm asked if it's continuous at x equals negative 1/2 or x equals 1, I know that it's not going to be continuous at those values. If I was looking at a graph, I can see my vertical asymptote here and a hole here. So I can see that I literally would have to jump over this asymptote if I were trying to draw this graph without picking up my pen, right? So because I'd have to jump right over that asymptote and I can't draw from one side to the other, it's not going to be continuous there. Although we understand that is true from looking at the graph, what we're practicing is this 3-part explanation definition proof of whether or not it is, because here we're starting to talk calculus, which is what we'll need to do next year on the calculus exam if we're headed to that class. Okay, let's see what's up next. Okay, I want you to try this next problem like a whiteboard problem. So I want you to take a look at this function and that just tells me it was page number 3. Don't worry about that. I just don't want to get my pages mixed up. Okay, so for this function, I want you to decide if it's continuous at x equals 1, and then as a separate problem, decide if it's continuous at x equals 2. Remember, whether or not we can tell that by looking at it, I still have to go through this 3-step process of showing that it is or is not continuous. So pause it here, try those, come back and we'll check them together. Okay, what did you decide? Let's see. So is it continuous at x equals 1? So I'm looking for f of 1 as my first part. So I'm plugging in 1 here, 1 minus 2 over 1 squared minus 4. 1 minus 2 on top gives me negative 1. On the bottom, 1 minus 4 gives me negative 3. So 1/3. We're good. We actually have a function value at x equals 1. It means if I looked at x equals 1 on my graph, I would see an actual point for that x value. Now let's look at the limit. Well, if we're allowed to plug in by direct substitution, I should try that first. I should always try it first, right? If nothing funky happens when I try to plug it in, then I'm good to go. I already did direct substitution here when I found the value of the function at x equals 1, so we know it's going to work out. So let me just do direct sub here. 1 minus 2 over 1 squared minus 4. I already saw that gave me 1/3, so we're good. So the function is defined at x equals 1 in part A. The limit exists in part B. And now for the third part, to see that it's continuous, I have to show that those two values equal each other. And they do, they're both 1/3. So this tells me on my graph, at the x value of 1, I have a y value of 1/3. This part tells me if I graphed it and I looked at the left and right hand sides, as I got closer and closer to an x value of 1, I would see I'm getting close on both sides to a y value of 1/3. So I'm getting close to the actual y value where the point will be. So yes, I'm going to say that f of x is continuous at x equals 1 because these two parts equal each other. Because f of 1 equals the limit as x approaches 1 of f of x, which is equal to 1/3. Ta-da! Do you hear my dog panting over there? Kenai, what's the problem? Why are you so upset? Oh, there, come on in, Kenai. Oh, there she is. Why are you so upset, Kenai? She's like a princess. Okay, so let's do the same check to see if it's continuous at x equals 2. So first of all, is it defined at f of 2? Let me plug in 2 minus 2 over 2 squared minus 4. Oh, it's not looking good. Now what we see is that we would get 0 over 0. Notice I'm not making it equal to 0 over 0 because nothing can equal this value because it's not defined. So I'm saying that it would imply that. So I'm not going to find the limit. I fail right here. So is it continuous? It's not continuous at x equals 2 because f of 2 is not defined. Or I could say f of x is not defined at x equals 2. Both of those phrasings would be just fine. Okay, so let's talk about where I have to be careful about continuity because there are lots of functions, polynomial functions, for example, which are continuous everywhere. So when will I have to be worried about continuity? There are two places that I have to watch for. So if I have a function, I want to look where the function has points of discontinuity itself. So we're looking for where our denominator equals 0. We're thinking like in a rational function. Where would I have a vertical asymptote or a hole? Where does the denominator go to 0? The other place I have to be careful of is when I have piecewise functions. I want to look first to see if there's any discontinuity on each piece. So look at each of those pieces on their own and think, is there a place that it has a denominator that goes to 0? If it's okay by that, check. Then the other thing I have to look at is where I jump from one piece of the piecewise function to the other piece, that x value where I move from one to the other, is it continuous there? So we'll have to do a check at those kind of jumping breaking points between the pieces of the function. So for example, let's say we have this function f of x right here, and our instructions are to determine for what values of x, if any, the following function is discontinuous. So I want to see where it's discontinuous, but we're seeing it's totally possible that we might find that, that it's continuous everywhere. So the first thing I want to check is, do any of these three parts on their own have a point of discontinuity? So I'm thinking, is there a denominator for any of these that could go to 0? Nope, we're okay on that check. So each of those three functions on their own are continuous everywhere. So now what I'm worried about are the values where I jump from one piece to the next. So right here, when I have all the x values up until and including 0 on this top piece, and then I jump to the middle piece for everything to the right of 0. So I'm worried about x equals 0, my continuous. And then I see here, this function covers everything from just to the right of 0 all the way up until and including 1, but then everything to the right of 1 is on this piece. So I'm worried about 1, where I move from the middle piece to the bottom piece. So I have to check for discontinuity at x equals 0 and x equals 1. Okay, so let's see. So I've got two different problems here. I have to check for continuity at x equals 0 and then check for continuity at x equals 1. So let's check at x equals 0 first. So you remember we've got a three-part check here. Is f of 0 defined? So I want to find the function value here at x equals 0. Now I want to think, which piece of the function am I on where x equals 0? X equals 0 is in here, right? X is less than or equal to 0. It's included right here. So I'm plugging in right here 0 plus 2. So the function is defined at 0. It has a function value of 2. Now, is the limit, does the limit exist? Now, because I have a piecewise function, and because at 0, where I'm looking for the limit, I'm jumping from one piece to the next, I have to make sure that the left and right hand sides as I approach 0 are approaching the same value. So I'm looking at the left limit as x approaches 0 and the right limit as x approaches 0, and then I'll compare and make sure they're going to the same place. So if x is approaching 0 from the left, then I have x values that are less than 0, right? X values that are less than 0 are in here. So I'm going to plug 0 in right here, 0 plus 2. So the left-hand limit is 2. The right-hand limit, so now we're talking x values that are to the right of 0, which means these x values are bigger than 0. X values just a little bit bigger than 0 are going to be on this piece of my function, right? So that's just 2. So I compare those and see that we're good. The left-hand limit is equal to the right-hand limit. The limit as x approaches 0 from the left is equal to the limit as x approaches 0 from the right. They both equal 2. So the limit as x approaches 0 of f of x exists. Yay, so we're good on the second check. Now the third part, we need to conclude if it actually is continuous at x equals 0. It's continuous if the function value is equal to the limit, and it is. So, is it continuous? Yes. F of x is continuous at x equals 0 because f of 0 is equal to the limit as x approaches 0 of the function. All right, now remember the question asked us at the beginning on the previous page of notes I had there. It said, find the values of x, if any, where it is discontinuous. We just showed that it was continuous here. They only care where it's discontinuous. So we have to do this work, but if I look in the back of the book, it's not gonna say x equals 0 because it wants to know where it's discontinuous, and I just showed that it is continuous at x equals 0. So I have to show this work, but I'm not going to see this value as an answer. So now, the other value I had to check, the other place where it could be discontinuous, is at x equals 1. So I've just rewritten the function here so we can see it again. Let's do our 3-point check, or 3-part check. So f of 1, let's see, 1 is on this piece of the function right here. So I'm using this part of the function rule, it's equal to 2. Now the limit as x approaches 1, because 1 is a point where I jump from one piece to the other on a piecewise function, I have to check that limit by finding both the left and the right hand limits separately. So the left hand limit as we approach 1, that means our x values are less than 1. That's going to be in here. So that's 2. Now the right hand limit. So if I'm on the right side of x equals 1, then I have x values that are more than 1, which means I'm on this piece. So I'm going to plug in 1 here. 1 squared plus 2, gives me 3. So I notice that the left and right hand limits don't match. That means that the limit does not exist at x equals 1. The limit as x approaches 1 of f of x does not exist because the left and right hand limits don't match. X approaches 0 from the left does not equal the limit as x approaches 0 from the right. So what we can conclude there is that it's not continuous at x equals 1. Because the limit as x approaches 1 of f of x does not exist. And we have to pass all 3 parts of that test, and because we failed one of those parts above, I don't even get to check to compare if they're equal to each other because we failed in the second step, right? Does not exist. All right, let's try one. I want you to, just like a whiteboard problem, I want you to look at this function and decide for what x values, if any, the function is undefined. So the first thing I want you to do is think, where does this function have the potential to be discontinuous? Oh, I didn't mean undefined, I meant discontinuous. There we go. Okay, so the first thing I want you to think is, At what x values does it have the potential to be discontinuous? Are there any denominators that could go to 0? Is this a piecewise function where I have to check the x values where I jump from one piece to the next? So to find all the places where it's possible to have discontinuity, and then check each of those x values separately. So you're taking a minute to pause, to pause here and do that work, and then come back and we'll check it together. Okay, so hopefully you have done that and you're returning now to talk about all the answers you got right. So the places where you're going to check, the first thing we notice, there are no denominators here that could go to 0, so I don't have to worry about discontinuity for that reason, no holes or asymptotes. But because it's a piecewise function, I do want to check the x values where I'm jumping from one piece to another. So I'm going to check x equals 0. I'm going to check x equals 2. I'm going to do those separately. So let's check at x equals 0. The first thing I'm looking for is whether that function is defined at x equals 0. Let me see if I can get the whole thing in here. Okay, so if x equals 0, we're on this piece of the function, right? So the function value is 2 times 0 or 0. So we're good, it is defined. Okay. So the next thing I want to check is to see if the limit exists. Now, because we're talking about a piecewise function and we're checking the x value 0 where I jump from one piece to another, I have to compare the left and right limits. So the left-hand limit, where x is, or to the left of 0, that means x's are less than 0. I'm on this piece, so 2 times 0. The left-hand limit is 0. Now the right-hand limit. The right-hand limit is where my x values are bigger than 0, so I'm on this piece right here. So I'm going to plug in 0, 0 squared plus 1. Oh, that's not looking good, is it, guys? So what I notice here is the left and right-hand limits do not agree. So the limit as x approaches 0 does not exist. I fail right here. Is it continuous at x equals 0? I will say no, because the limit as x approaches 0 of f of x does not exist. All right, so the other place you saw that there might be a problem was x equals 2, where you jump from one piece to another. So I have to do the 3-point check there as well. So let's find the value at x equals 2. So at x equals 2, I'm on this piece right here. So I'm plugging in 2 squared plus 1. 2 squared plus 1 gives me 5. So the function exists at x equals 2. The next thing I'm looking for is the limit as x approaches 2. Because 2 is a place where I'm jumping from one piece to another, I have to be careful to check the left and right hand limits and make sure that they agree. So the left hand limit, where x's are less than 2, that's going to happen right in here. So I'm on this piece, 2 squared plus 1. 2 squared plus 1. So 5 is the left hand limit. The right-hand limit is where I have x values that are greater than 2. To the right of 2 is greater than 2. So I'm talking about this piece right here. So I have 7 minus, I plug in the x value, 2. 7 minus 2. Ooh, that looks good. Yay. So what I see there is that because the left and right-hand limits are the same, the limit exists. So the limit as x approaches 2 of f of x, here gulping down water, is equal to 5. I feel like you probably have teachers that have very small children who do not interrupt their lessons as much as my old lady dog does. Okay, so is it continuous at x equals 2? The function exists at x equals 2. The limit, or the function is defined at x equals 2, the limit exists at x equals 2. Are those two things the same? Yes. So, yes, because f of 2 is equal to the limit as x approaches 2 of f of x. They both equaled 5. Now remember, the way this question was phrased at the beginning, determine for what values of x, if any, the function is discontinuous. So what we see is that it was discontinuous right here at x equals 0, but it was continuous at x equals 2. So x equals 2 is not going to be one of the answers because I checked and it was continuous. They want to know where it's discontinuous, so the answer is x equals 0. Okay, there's one more thing for us to think about here. Let's suppose that we were asked, same kind of question. We want to know for what x values, if any, this function is discontinuous. So the first thing I want you to notice is, well, it's a piecewise function, so I'm going to want to check what's happening at x equals 2, just in the same way that we have on the couple problems we just did. But the other thing to consider is that this piece of the function itself is a fraction. So what value are we worried about for this piece of the function? Where would it be discontinuous? Yeah, at x equals 3. 3 in the denominator is a problem there. It would cause that function to be undefined. Now, is it really a problem? I'm worried about where x equals 3, it being undefined. But look, this piece of the function we only use for x values that are less than or equal to 2. So an x value of 3 isn't even going to be on this part of the graph. So I'm not worried that this would be discontinuous at x equals 3 because it's not going to show up on this part. X equals 3 is going to be on this part of the graph where it'd be okay. So the only thing I would want to do here is check where I change pieces. So I would check to see if it's continuous at 2. And I'm not going to do that with you because it's just like the last couple problems that we did, so you don't need to see it again. But I wanted to mention that I do want to check denominators to see if they are a problem. Okay, so here's our assignment, guys. Make sure that for each of those, whether you can tell right away that it's continuous or not, remember that your job is to show that 3-part check.
Guess what? That was our last new material for this class. That was our last lesson. So all that we have left is a review for 11.1 through 11.3, and then an assessment, a little kind of in between a quiz and a test. I think I put 10 problems on it. So next week you'll have a review, and then you'll have a little assessment, and then we're done. So if you are a junior, I hope that you have a wonderful summer. If you're a senior, man, it really stinks that we're ending this way, and I'm sorry that we can't say a proper goodbye, which I hope means that when you're home from college, or if you are staying local for college, that you'll stop by and visit us and say hello and tell us all the great things that are happening for you. So like I said, review, assessment on 11.1.11.3, and then we're done for our class. The last week of class is kind of like a catch-up makeup week. So I won't have any new material. If you're all caught up and you've taken that assessment, then you're done with my class. Spend time making up stuff from another class. Okay? Have a wonderful summer, guys. Stay safe. I miss you. Bye.